In the circuit on the page, we have a path here where there is no potential source, and we have another path that has a potential source. So we're going to look at what happens when I turn this switch on to engage this power source. And let's say that we have an initial current flowing here of I naught going through this inductor. So using Faraday's law, we go around this loop. And remember, Faraday's law says that the integral of the electric field dot differential length is equal to the inductance times the change in current with respect to time. So let's write this equation. Starting here, I'm going to have the way the current is flowing. Notice I have plus minus with a battery. Those are always the same. Plus minus with the resistor. The way a current's flowing from left to right. So I'm going to write V naught minus I function of t times R, and that's because I have an electric field in the battery and I have an electric field in the resistor. So now this is going to equal the induced potential in the inductor. So that's going to be L d I function of t over dt. And now I can rearrange this equation to put everything on one side and current on the other. So I'm going to have L di function of t over dt plus it I function of t times R, and that's going to equal V naught. Now since this is a first order equation, I can take and split it, and to do that I'm going to go through by dividing by L, and since I divide one side of the equation by L, I have to divide the other, and I can bring this I function of t times R over L, and I'm going to take that to the other side. Put it together with common denominators, and now I can do my split. And I'm going to do the integral. On the left hand side, my integration limits are I naught to I function of t. and that's going to be the integral from 0 to t dt over L. Now on this left-hand side, I'm going to have the natural log of v naught minus I function of t times r, and I'm going to divide that by negative r for my chain rule. And on the left-hand side, integral of dt over r is just, dt over L is just t divided by L with the limits of 0 to t. Now I can transfer this r up to the other side and put my limits of integration in. And now I can put these two logarithms together. And I'm going to put the r in the denominator because we're going to have a value or a variable for this. And now I can take the exponential of both sides, and I'm going to get v naught minus I function of t times r over v naught minus I naught times r, and that's just e to the negative t over L divided by r. Multiply out. And I'm going to subtract VO from both sides. And if I subtract VO, I didn't mean to write VO, I meant to write I function of t here. And that's negative t over LC here, or L divided by C. I'm sorry, L divided by R minus V naught. And when I bring the negative through, and I can divide by R, And now here I need to determine, well, what's V naught divided by R? Well, V naught divided by R would be the case of if I just ignored the inductor. So if I just took this out and connected it up, shorted it out, then what V naught over R is going to be is just the maximum current that can flow, because at a certain point this inductor is going to act like a short circuit. And so the only current that's going to be flowing is based off of just the voltage supply and the resistance. So I can name this new variable I max. And now we can see that we have I max is equal to VO over R, and L over R is what we call tau, or timing constant, and it relates to RC in the capacitor charging circuits. And we see the similarities between the capacitor and the inductor. For the capacitor charge, it was V function of t is equal to, we had it as E for our battery, minus E minus the initial voltage on the capacitor, E to the negative t over RC. So we see the functions very similar. I max relates to the supply in the voltage, or in the capacitor case, and V naught and I naught are related. V naught referring to the voltage across the capacitor, I naught related to the current through the resistor, and we have these tau values that function the same way, in that it takes 5 tau to completely charge or discharge. So there are very good similarities. It should make it easier when you're using this formula to kind of base it on what we did with the capacitors.